Hello, welcome to this video. In this video we're going to be exploring what a symmetry is in physics and how this relates to conservation rules, bringing everything together to talk about Noether's theorem. Noether is that woman of whom you can see a photograph of on this PowerPoint. And Noether is one of the great female figures in physics, so very worth doing a video about the physics surrounding Noether's theorem, symmetry and conservation rules. So if you've done a fair bit of physics before, one thing you'll know that we love doing in physics is maximising or minimising quantities. So when we found out about the dynamics of Newton's laws, one thing we could not help but to do was to get to some mathematics that Newton's laws implies, where we are once more maximising or minimising something. However, when we try to do this with Newton's laws and trying to get something that will predict the equations of motion through optimization techniques, so the maths or calculus behind maximising or minimising quantities, we found something mildly surprising. The thing we have to maximise or minimise, in other words find the stationary value of, is not a function. It's an integral of a function. Now we call integrals of functions functionals, and the functional that provides the classical equations of motion is called the action. And the thing this functional, the action, is an integral of is the Lagrangian. Now, the Lagrangian really contains the physical part of our system. The Lagrangian is based on the energy of our particle, and in a little bit we'll mention how we generalise this idea to fields, but for now let's stick with the classical particles. So the physics is within the Lagrangian, but if we're worried about symmetries, we're worrying about altering the mathematics such that the dynamics don't actually change. So if we're worrying about symmetries, we are worrying about the action itself, so the integral of the Lagrangian. So to summarise what is said mathematically, we have an action which is the integral of the Lagrangian over time, and we get the equations of motion by considering a form of the Lagrangian such that when we alter the Lagrangian a tiny bit, say by shifting the position of a particle a tiny bit, that doesn't actually alter the action itself. So that's what we do if we've got particles. However, if we've got fields, we can't really talk about the kinetic or potential energy of a field at a point, because fields are distributed across space. So we need something that will really tell us about the energy density of the fields. And the quantity that describes energy density, or is in terms of the energy density, is a quantity called the Lagrangian density. And as you might guess, if you integrate the Lagrangian density over space, so over our 3 dimensions of space, which is why we've got d3x, it means we're integrating over all the dimensions of space, then we get the Lagrangian, so if you like, a quantity about considering the total energies of our field. But the other beautiful thing with defining the Lagrangian density is if we substitute our equation for the Lagrangian in terms of Lagrangian density into our equation for the action, we can define the action in terms of the Lagrangian density, but now we're integrating over space-time, over all the dimensions of space-time. Because we have to integrate over d3x and dt, so we're integrating over the 4 dimensions of space-time. And this allows us to talk about classical mechanics, for example, in a relativistic context, so within the setting of space-time, in a way that the original formulation of Hamilton's principle of least action, which concerned the Lagrangian, not the Lagrangian density, simply didn't really allow us to do. And we'll talk more about the Lagrangian density on the next slide. And seeing how we can generalise the statement that delta S is 0 to fields using the Lagrangian density. But a quick thing to note is you might note I put squiggles. I can't remember their technical name, so for this video I'll just call them squiggles above the lower and upper limits of our integral, and I put those squiggles because the upper and lower limits are points in space-time, so they're like the tips of 4 vectors. And I used those curly bars, if you like, to indicate that these are coordinates in space-time, so tips of 4 vectors rather than tips of 3-dimensional Euclidean vectors, which is and that kind of style is a semi-common style you see in physics. Now, whereas if we're talking about a particle, as I said, we can talk about the kinetic and potential energy of a particle. We can't really do that with a field. We have to talk about kinetic and potential energy density. But also for a field, the dynamics is given by how the field changes with time. We're interested in a description of how the field lines as a whole vary, and we can get the field lines by looking at our equation for the field itself. Because the field lines just point along the maximum rate of change of the field. So if we have an expression for the field, we have an expression, or can get an expression for the field lines. And so, whereas the Lagrangian is going to depend on the position and velocity of a particle, the Lagrangian density, applying it to a field, will depend on the field and the derivatives of the field. And we tend to use the symbol phi for the field, and when we're looking at fields in the context of relativity, they're fields across space-time. So they're scalar functions of, of either, 4 vectors themselves or components of 4 vectors. Because we're dealing with fields in space-time, there's 4 derivatives of a field. The time derivative and our 3 spatial derivatives, and we use the index mu to indicate what derivative we're talking about. And the dynamics of the field are still given, or can still be given, by insisting that the action is minimal or maximal. The action is essentially stationary. During my videos I might sometimes say we minimise the action. In some cases it might turn out that we want to maximise the function. Maximise the functional, but to be honest, the important thing is that our functional S is stationary when we shift the Lagrangian a little bit, about the function that expresses the Lagrangian that physical systems actually follow. And now we've talked about this kind of overarching bit of mathematics, if you like, in fairly qualitative detail, we're ready now to talk about symmetry. So we get an equation of motion by essentially finding some, it's a constraint on the form the Lagrangian or Lagrangian density can take, such that the Lagrangian acts to minimize or maximize our function or the action. Now, if we can find a way to shift the Lagrangian a little bit, in a way that results in the same action, then by definition this shift in the Lagrangian won't impact the idea that the Lagrangian should minimise the action, because our new Lagrangian is given the same action as the old Lagrangian. And therefore the bit that we can add to our Lagrangian that won't change our action is called a symmetry. Now, there are more exotic kinds of symmetry we can have, but for this video we're just worrying about symmetries that don't change the action. They do change the Lagrangian, so they are altering the system in some way, but because they don't alter the action, and the dynamics come from trying to minimise or maximise the action, these changes don't actually impact the dynamics of our system in any way. And so these kind of changes are symmetries. And, the symmetries are going to be expressed in terms of our field, if we're looking at, symmetries for a field. And a lot of these symmetries you will have probably already been familiar with. I mean, one symmetry for a field in the context of relativistic field theory is a symmetry which is essentially the if you like, the Lorentz transformations of a field, and that leads to the idea that the centre of mass of a field doesn't change with time if our field is free and non-interacting, which leads to the idea that non-interacting particles have a quantum property called spin, which is conserved. So the idea of symmetry is very important in physics and does lead to conservation laws. Before we talk a little bit more about the role of symmetry, let's have a go at finding a very common type of symmetry, which you can get rather self-evidently from the statement that a symmetry is a shift to a Lagrangian which doesn't change the action that the Lagrangian is corresponding to. Now, we said we were going to mention a fairly common symmetry, and if you think that the action is an integral of some function over space-time, you might already be able to immediately guess how we could alter the function without changing the action, based on the idea of derivatives and integrals cancelling out. But it's worth going through in a bit of detail because this symmetry comes up a fair bit in physics. So, the symmetry, we're going to be showing today is a symmetry, is a shift we can make to our Lagrangian density, and this shift is the divergence of some 4-vector field. So it's some measure of how, much the field is kind of like, is either getting stronger or weaker, if you like to think of it like that. But that showed that this divergence is a symmetry. Well, as a reminder, if the divergence is a symmetry, then when we add it to our Lagrangian to get, well, I should say Lagrangian density to get a new Lagrangian density, the new action should equal the old action. But if we're going to show that's true, we need an explicit equation for our new Lagrangian density, which is just the old Lagrangian density plus the divergence of our vector field, F. And using that, we get that the new action is the old action plus the integral of our divergence of our vector field F integrated over space-time. And whenever you're seeing something in the context of space-time for the first time, it's often useful to imagine, on a mathematical basis anyway, that just for a moment, that space-time is really just one-dimensional space. That's all there is to it. Just to make the maths easier to work out, what's going on. Well, if space-time is one dimension, let's say the x spatial dimension, then the bit in blue that we're adding to our old action S to get our new action S prime would be just the integral of df by dx times dx. And the derivative by dx and the integral by dx cancel each other out, meaning that we're left with evaluating our function f at the lower and upper limits. And a similar thing applies if we're dealing with space-time, providing the partial derivatives as partial derivatives over all our space-time coordinates. And we're integrating over all our space-time coordinates. The integration and differentiation cancel each other out. That's why we sometimes call an integral an antiderivative, because they in some ways cancel. In some ways they're inverse operations. The constants of integration means it's not quite strictly true to say they're inverse operations, but they do cancel each other out, at least in the case where our integrals strictly have limits. And let's consider what those limits would be. Well, the upper and lower limits of our integral in blue are going to be 4 vectors. Because our integral is over space-time, so the upper and lower limits are going to be essentially coordinates in space-time. So mark, if you like, the tips of 4 vectors. And they're called one 4-vector x1 and the other 4-vector x0. And here is where we start to go into the realm of assumptions, because, in relativistic field theory, we're interested in fields which extend across all of space-time. Now, I don't know about you, but I personally have not been at the edges of space-time ever. And so we can't really easily empirically test what are the fields on the boundary of a space-time. However, we know from forces, which are kind of vector fields in Euclidean space, that those forces die away as you go to infinity and go to the edges of the space. And we presume, we really build it into the theory that something similar happens with quantum fields or with relativistic fields. Whether that is valid is a matter open to debate, but we're going to run with that assumption. And that means our upper and lower, well, when we put our upper and lower limits into f, we're going to get 0. Which means that if we look at our expression for the blue integral is just 0, so the new action is the same as the old action. And therefore we found something that we can add to the Lagrangian, therefore it is corresponding to some shift in the energy densities of our fields at a particular point in space-time, but which doesn't affect the way that the field is acting. It's shifting the field in some way, but it's not changing its behaviour, because we're still minimising our action just as we were before. So the change in the Lagrangian doesn't have any, physically measurable, observable effects, even if we can visually see that this shift has occurred by having some image of the old field and some image of the new field. And therefore the shift is a symmetry of our field. It would be a shame to kind of finish this video without at least trying to explain why symmetries are so important in physics. Symmetries are important in mathematics because they describe changes we can make to a mathematical object, or something we can visualize from that mathematical object that doesn't change the fundamental, if you like, algebra of that object. The similar thing is true in physics. However, instead of the algebra of a mathematical object, we have the dynamics of the system. And therefore, a symmetry implies that there is some shift we can make that isn't changing something about the dynamics. And that naturally leads to the idea of some kind of conservation. There is something being conserved during this shift that is ensuring that the dynamics don't change. And that's in nuts and bolts what Noether's theorem is. Now, strictly, it's also a way to predict a conservation law from a symmetry, but as well as that, it's the statement that a symmetry implies a conservation law. So for every symmetry, you have a conservation law. And so, you could do it in reverse, but equally, if you get a field and you're doing a bit of theory and you want to know some properties of the field, you can just use Noether's theorem, if you understand your field well enough, to work out the conserved quantities. And the beautiful thing is, you don't even have to know of those conserved quantities beforehand to predict them for your field. And so, for example, we can know things like isospin might be conserved in some cases, based on a field, even if we had no prior idea what isospin was. We can look at Schrodinger's equation, and from that infer something about a Lagrangian-like thing for the wave function, and then work out some symmetry within the wave function, which will probably correspond to the probability within the wave function not changing with time. So, symmetry and conservation laws are vital to physics. And they're very, very much interconnected, as one would expect based on the definition of asymmetry. But anyway, that's everything for this video. I've done another video, which I'm hoping to release around the same time as this one, on Hamilton's principle of least action, where, I say that, whereas unlike Noether's theorem, which isn't a particularly trivial statement, to an extent Hamilton's principle of least action is trivial in the way it's formally phrased, despite the principle being quite useful. So if you would like something a bit more philosophical about the nature of physics, possibly, maybe check that video out. But I hope you got something out of this video, and I'm wishing you a lovely day ahead.